What happens when the planet you thought you understood begins to behave like a stranger? Picture a quiet control room where the screens never sleep. Somewhere, an analyst watches thin lines of data crawl across a map of the Earth. Numbers that represent winds, tides, temperatures, magnetic readings. The lines usually drift the way they always have. Slow, seasonal, familiar. But lately, some lines have started moving with a nervous urgency, as if the planet itself has changed its pace. Outside that room, life continues with its ordinary confidence. Kids walk to school. Planes arc across the sky on invisible highways. Ships aim for ports, as if the ocean were a dependable road. Migrating birds stitch their ancient routes from continent to continent. All of it depends, quietly and constantly, on something we rarely name out loud: the assumption that Earth is stable enough to plan on. And yet, there are moments, rare, unsettling, when stability stops feeling like a fact and starts feeling like a belief. This story begins in those moments, not with a single catastrophe, not with a single headline, but with a collection of puzzles, reports of patterns that appear to be shifting too quickly, or behaving out of character, or refusing to match the neat explanations we lean on when we talk about how nature works. A compass that no longer points where it used to. Moisture moving in ways that seem improbable. Ocean behavior that feels less like a clock and more like improvisation. Regions that warm and cool in contradictory layers, as if the ground were arguing with itself. Bursts of electrical activity high above the atmosphere that don't seem to follow the usual rules of cause and effect. If you listen closely, you can hear the deeper question beneath all of it. Are we witnessing new phenomena, or just discovering how much we never understood? For decades, we've built an astonishing, delicate relationship with models. Models of weather, models of oceans, models of carbon cycling through forests and air and sea, models of the planet's magnetic shield, the invisible armor that turns solar violence into auroras and radio static. Models are our best attempt at humility, an admission that we can't hold the whole world in our heads, so we translate it into mathematics and simulations, into forecasts and probabilities, into systems that can be tested and revised. But models also create a kind of comfort. They let us believe the future will arrive in recognizable shapes. Then the data arrives with new shapes. Consider the idea of a pole, not a wooden post in the ground, but a point on a map that seems as fixed as a star. The magnetic North Pole isn't the geographic top of the world. It's a restless coordinate generated by currents deep within Earth's molten interior. It drifts. It has always drifted. But what if it begins to race? What if it moves fast enough that navigation systems have to be corrected more often than expected? As if the planet's internal compass is being rewritten mid-sentence. Or consider a river, one not carved into soil, but suspended in air. Atmospheric rivers are real, recognized, powerful, long corridors of water vapor that can carry enormous moisture from oceans to land. They are part of our new vocabulary of extremes. But what if similar structures are reported over places that seem to lack the very ingredients those structures normally require? What if the sky behaves as though it is borrowing water from somewhere we can't easily see? And then there's the ocean, the Gulf Stream, and the great currents that move heat across the planet like blood through an artery. We talk about them as steady forces, even when they wobble. But what if instruments suggest segments behaving in chaotic, unexpected ways? Eddies born and fading, directions that appear to misbehave, ecosystems responding as if the ocean's logic is changing. These are the kinds of claims that make scientists cautious, and rightly so. Sensors fail, data can mislead. Our perception craves patterns, even in noise. And yet, the human mind has another instinct, just as strong as skepticism, the instinct to look again when something doesn't fit. That's where we are now, standing in the doorway between doubt and wonder. This documentary is not a courtroom. It is not here to convict the planet of wrongdoing or to turn uncertainty into spectacle. Instead, it's an exploration of the space where knowledge meets its edges. A journey through 10 reported anomalies, each one a story about observation, interpretation, and the uneasy beauty of not knowing. Because the truth is, Earth has never promised to be simple. We inherited a world older than memory, layered with forces that don't require our permission. We learned to predict enough of it to build cities and flight paths and calendars. But beneath that achievement lives a quieter reality. The planet is not a machine designed for our comprehension. It is a living system in motion, a conversation between rock and water, and air and electricity, sometimes fluent, sometimes cryptic. So let's begin with a single guiding question. If the world is changing in ways that surprise us, what is it asking us to reconsider? Our science, our assumptions, or our sense of certainty itself? What if the very thing that helps you find your way, an invisible arrow in the sky, started to slip out of place? Imagine an old-fashioned compass in a gloved hand, the needle trembling as it searches for north. For centuries, that needle felt like a promise. Not just direction, but reassurance. Even when storms hid the stars, even when the horizon became a blank line, there was still a point on Earth that pulled you home. But magnetic north is not a mountain. It is not a landmark you can photograph. It is a moving idea, an emergent point created by swirling currents of molten iron thousands of miles beneath our feet. The Earth's outer core turns and churns like a slow ocean of metal, and in that motion, magnetism is born. Most people don't notice this because the movement is usually subtle. A drift, measured in miles over years, corrected quietly in navigation charts, baked into the invisible math of aviation and shipping. The planet does its slow work, and our technology adjusts in the background. Then, in the modern era, the drift began to draw attention. Measurements suggested the magnetic North Pole was accelerating, moving across the Arctic at a pace that felt less like gentle wandering and more like urgency. Not panic, but speed. The kind of speed that forces people who never think about magnetism to suddenly care. This isn't just trivia for geophysicists. Magnetic north is a key ingredient in global navigation. It influences compass readings, and those readings still matter, especially in places and situations where satellite signals are weak or compromised. Even GPS systems rely on a layered infrastructure of reference frames and corrections, many of which lean on accurate models of Earth's magnetic field. At a certain point, the corrections have to be updated more frequently. The world, in a sense, needs a new definition of north. There's something psychologically unsettling about that. We tend to treat north as if it belongs to geography, as if it's embedded in the bones of the planet. But magnetic north belongs to the core, and the core is dynamic. It does not hold still for our maps, so what could make it move faster? One possibility is that the outer core is shifting in patterns we don't fully observe. Jets of liquid iron changing speed, regions of magnetic intensity strengthening here while weakening there. Another is that what we interpret as movement is the surface expression of a more complex rearrangement, an internal tug-of-war between competing magnetic patches. In a way, the pole's motion is a symptom, not the disease. It hints at a deep interior life, a reminder that beneath the crust, where we build houses and highways, the planet is still in the act of becoming. And there is a second layer to this story, one that turns an interesting geophysical detail into something more existential. Earth's magnetic field does more than point compasses. It acts as a shield, deflecting charged particles from the sun. It shapes the space weather that can disrupt power grids, radio communication, and satellites. It creates the auroras, those curtains of green and violet that make the sky look like it's dreaming. If the magnetic field changes, the shielding changes. Not necessarily dramatically in a human lifetime, but enough to matter in the long arc of history. That thought can pull you toward alarm, and it's important to resist easy drama. The planet's magnetic field has shifted many times before. It has weakened and strengthened. It has even reversed in deep time, flipping north and south like a slow planetary heartbeat. Life endured those shifts. The world did not end. Still, there is a difference between not apocalyptic and not meaningful. Even if the drift is a normal part of Earth's magnetism, its speed raises questions about our ability to keep pace, scientifically and practically. We are living in an era where the planet is being measured with unprecedented precision. That precision reveals changes we might never have noticed before. It also reveals how much motion was always there, hidden under the illusion of permanence. In the Arctic, the magnetic pole doesn't announce itself with a flag. It simply continues moving, indifferent to our need for fixed points. Researchers chase it with instruments and satellites, updating global models so that navigation systems remain trustworthy. It's a strange kind of pursuit, humans trying to keep track of a point that isn't a place. And perhaps that's the first lesson of this journey. Some of the most important anchors in our lives are not anchored at all. So here's the question to carry forward. If North can drift, what other certainties are quietly in motion beneath our feet? And how many of them have we mistaken for permanence simply because they moved too slowly for us to notice? What if the sky could carry a river where no river should exist? There are nights when the air feels heavy, not with heat, but with intention, when clouds gather as if following a script written far beyond the horizon. Then suddenly, rain arrives in a way that doesn't feel like weather. It feels like delivery, a concentrated shipment of water released with almost mechanical focus over a narrow corridor of land. Meteorologists have a name for this: atmospheric rivers. Despite the poetic sound, an atmospheric river is not a metaphor. It's a measurable structure, long, narrow bands of water vapor moving through the lower atmosphere. When those bands collide with mountains or colder air, the vapor condenses into intense rainfall or snowfall. They can be life-giving, replenishing reservoirs, and snowpack. They can also be devastating, causing floods and landslides, reshaping coastlines and communities overnight. In the usual story, atmospheric rivers form over warm ocean water. They draw moisture like a sponge and push it toward land under the guidance of winds and pressure systems. The ocean is the reservoir. The atmosphere is the conveyor belt. But here's where the puzzle begins. There have been reports and discussions suggesting river-like moisture transport occurring over regions that seem, at first glance, less suited to that classic formation. Over inland areas, or in unusual seasons, or in configurations that appear to defy what people expect from the textbook narrative. Observers see the signature patterns: long plumes of moisture, intense localized precipitation, and ask, where did the water come from, and why did it arrive like this? To be clear, the atmosphere is not limited to one recipe. Moisture can be recycled. Water evaporates from soil, vegetation, lakes, and wetlands. It can be carried long distances and then pulled down by the right combination of temperature gradients and wind. Storm tracks shift. The boundary between ocean-fed and land-fed moisture can blur. Still, the feeling persists, especially for those living under these events, that something has changed in the choreography. In the past, people spoke of rain as a kind of weather luck. Now, it can feel like a hard-edged phenomenon. Too much, too fast, too targeted. A month of water falling in a day. A drought broken not by gentle relief, but by a violent correction. This is where the tension between discovery and doubt lives. Is the anomaly in the sky or in our expectations? Are we witnessing new atmospheric behavior, or simply the planet is expressing old capabilities under new conditions? When you measure the world more closely, you don't just find answers, you also find complexity. There's another dimension to this story that is easy to miss: the human relationship to patterns. For most of our history, weather was local. You looked at clouds, you felt the wind, you read the smell of rain in the air. Even when people kept records, the records were bound to a single place. Today, we watch moisture move across continents in near real time. We can see the invisible because satellites can map water vapor in the atmosphere like ink on paper. That new sight changes our emotional relationship to weather. It's one thing to get soaked by a storm. It's another to watch the storm's moisture pipeline approach your town days in advance, like an incoming tide. And when the plume takes an unexpected path, the mind reacts with a particular kind of unease. Not just fear of damage, but a sense that the sky is behaving with unfamiliar freedom. In climate science, unfamiliar does not automatically mean impossible. It often means the system has shifted into a different range of variability. Warmer air can hold more moisture, which can amplify precipitation extremes. Changes in atmospheric circulation can steer storms differently. Local land changes, deforestation, urbanization can alter evaporation and heat patterns, nudging weather in subtle ways that accumulate over time. But even with these explanations, the experience remains humanly strange: a river in the sky, appearing with a kind of precision that feels intentional, even though it isn't. If you've ever stood outside during one of these events, you know what I mean. The rain is not gentle. It has weight. It sounds like static and drumming at once. It erases the world into a curtain. It makes you feel small, not because it is loud, but because it is focused. The atmosphere all at once reveals its capacity to move water like a machine built for scale. And then it passes. The clouds thin. The air clears. The world looks freshly rinsed. But the ground tells another story. Swollen rivers, mud where streets were, trees tilted as if trying to leave. So what are we to make of it? Perhaps the anomaly is not that atmospheric rivers exist, but that we are only now grasping how powerful and adaptable they are. Perhaps what feels like defiance is simply the atmosphere responding to new boundary conditions: warmer oceans, altered jet streams, shifting pressure patterns, using the same fundamental physics it has always obeyed. And perhaps the deeper question is not about moisture at all, but about predictability. If the sky can organize water into corridors of concentrated force, how do we live with the fact that the planet's most familiar systems — rain, wind, seasons can assemble themselves in ways that surprise us. What does normal weather mean in a world where the atmosphere can rearrange its rivers overnight? What if the ocean's great heartbeat, the steady rhythm of currents that temper climates and feed ecosystems, started to skip a beat? Stand on a shoreline at dawn and watch the water long enough, and you begin to feel the ocean as a living thing. Not alive in a biological sense, but alive as a system, always moving, always exchanging, always pulling heat and salt and nutrients across vast distances. The ocean is Earth's memory. It stores heat. It absorbs carbon. It carries signals from one season to another, from one hemisphere to the next. It also hides its moods beneath the surface. From above, the sea can look calm, while below, currents twist like unseen muscles. Among those currents, a few are so influential they shape entire continents. One of them is the Atlantic circulation, including the Gulf Stream and related flows that carry warm water northward and return colder water southward at depth. This conveyor-like movement helps moderate temperatures in parts of Europe and North America. It influences storm tracks and rainfall patterns. It is not a single river of water, but a complex circulation, wide, layered, and sensitive. Now imagine hearing that this circulation might be changing, not collapsing overnight, not flipping like a switch, but shifting in ways that are difficult to pin down and even harder to explain to the public without triggering either panic or dismissal. Instruments suggest variability. Models suggest vulnerability. Headlines sometimes compress nuance into drama, and within that compression, the ocean becomes a symbol. Stable when we want stability, ominous when we need a story. The reality is more complicated and more interesting. Ocean circulation is driven by a mix of winds, temperature differences, salinity, and the geometry of basins and coastlines. In the North Atlantic, cold, salty water can become dense enough to sink, helping pull the circulation along. If surface water's warm, or if fresh water from melting ice and increased rainfall makes the surface less salty, that sinking can weaken. The system can slow, or its patterns can rearrange. This is not a science fiction scenario. It is a question scientists have studied for decades. What's haunting is not the existence of change, but the uncertainty around timing, magnitude, and consequences. And that uncertainty is itself an anomaly to people who crave clear answers, because we want the ocean to be a clock. We want it to do what it did last year, and the year before that, and the century before that. Our fisheries, shipping routes, coastal infrastructure, and weather expectations are all, in some way, tuned to what the ocean usually does. But usually is a statistical comfort, not a guarantee. Sometimes the ocean speaks in subtle shifts. A region warms while another cools. A current broadens. A deep water formation zone changes intensity. Sometimes the ocean speaks through biology. Plankton blooms arriving early. Fish migrating to new waters. Coral reefs bleaching under heat stress. Species appearing where they were never seen before. These changes can feel like anomalies because they are not singular events. They are slow-motion transformations with occasional spikes of drama, heat waves in the sea, sudden die-offs, storms that seem to feed on unusually warm water like fire on dry timber. One of the most unsettling aspects of ocean change is that it often hides behind averages. The global ocean can be warming overall, while certain regions behave in counterintuitive ways. A patch of cooler water can persist like a bruise in a warming sea. A sudden surge of warmth can appear off a coastline, disrupting marine life and weather patterns. To a human mind, these contradictions feel like broken rules. To a dynamic system, they may be the rules. Here's the philosophical thread running through this. The ocean's stability is not the absence of change. It is the ability of change to remain within a range that life and society can adapt to. When that range shifts, even gradually, our sense of the world's reliability shifts with it. That's why ocean circulation becomes such a powerful metaphor. It's a reminder that Earth's most massive systems we assume are too large to change quickly, can still respond to pressure in ways that matter within a single lifetime. And it's also a reminder of humility. We have remarkable instruments, floats, that drift through the sea, recording temperature and salinity, satellites that measure sea surface height and currents, sensors on moorings that listen to deep water like stethoscopes. Yet, for all this technology, the ocean remains partly unknowable, not because it is mystical, but because it is vast, layered, and full of feedback loops. In some regions, scientists debate what the data truly shows. Is a trend robust, or is it a phase of natural variability? Are we seeing a long-term weakening or a short-term oscillation? How do we separate signal from noise in a system that is, by nature, noisy? If you want to understand why people argue about climate science, start here, not in ideology, but in the ocean's complexity. The planet is not a simple equation. It is a set of intertwined processes, some slow, some fast, some visible, some hidden. And the ocean is the largest of those hidden stories. So tonight, if you find yourself near water, listen to the waves and consider what they don't tell you. Beneath that sound is a moving architecture of currents and heat, shaping storms you haven't yet seen and seasons you haven't yet felt. If the ocean's great circulation is shifting even slightly, what other systems are quietly adjusting with it? And how do we learn to live with a planet whose most powerful rhythms were never truly guaranteed? What if the warming world didn't warm like a blanket, but like a paradox, hot in one layer, cold in another, as if the atmosphere couldn't agree with itself? Most of us imagine climate change as a simple dial. Turn it up, and everything gets warmer. Summers intensify, winters soften, snow lines creep uphill, oceans store more heat. The story, in our minds, is linear. More greenhouse gases, more warmth. But the atmosphere is not a single room with one thermostat. It's a stacked cathedral of air, layered by pressure and temperature, stitched together by waves, winds, and invisible exchanges of energy. And sometimes, those layers behave in ways that feel almost argumentative. One of the most disorienting patterns people report is this: a winter that arrives with unexpected severity, or a cold snap that grips a region for days or weeks, even as the broader climate trend points toward warming. The headlines argue with each other. One day it's record warmth, the next it's historic freeze. The public hears contradiction and wonders if the science is broken. But contradiction is often the signature of a complicated system, not a failing one. In certain conditions, warming can rearrange circulation patterns in ways that produce intense cold outbreaks in specific places. The Arctic can warm faster than lower latitudes, shrinking the temperature difference that helps drive high-altitude winds. Some researchers describe this as a weakening or waviness in the jet stream, allowing cold air to spill south in deep loops. Others debate how strong that connection is, cautioning against oversimplified explanations. That debate matters. It's the difference between a confident story and a careful one. And yet, the experience remains visceral. Imagine stepping outside in a city that rarely sees deep winter, only to find streets iced over, pipes frozen, trees shattered by brittle cold. People ask, sometimes bitterly, how this fits in a warming world. The answer is that warming is not always less cold. Sometimes it's more energy, and more energy can mean more extremes, more moisture, more turbulence, more rearrangement. The climate system is not merely heating, it is transforming the distribution of heat. There's another, even stranger layer to the paradox. While the lower atmosphere, the troposphere, warms under greenhouse forcing, the upper atmosphere, the stratosphere, tends to cool. This can feel counterintuitive, like finding frost in the attic while the living room overheats. But it reflects how greenhouse gases trap heat lower down, while allowing the stratosphere to lose heat to space more efficiently. Why does that matter for our lived weather? Because the stratosphere influences the patterns below it. When the stratospheric polar vortex weakens or distorts, it can disrupt the usual containment of cold air near the poles. Sometimes that disruption cascades downward, reshaping weather for weeks. It's a reminder that weather is not just what happens around you. It is a conversation between layers of sky. And then there are the inversions, those moments when cold air settles near the ground, while warmer air sits above it, like a lid. Inversions can trap pollution, create eerie fog, and make valleys feel like bowls of glass. They can also amplify the sense of climate behaving oddly. The mountain is mild, while the town below is freezing. The sunlight bright, but the air biting. To a planet, these are dynamics. To a person, they feel like contradictions you can breathe. There's a cultural tension here too. We want climate stories to be morally clean. Warming is bad, cooling would be good, and change should be obvious. But the climate system doesn't arrange itself to match our storytelling needs. It delivers complexity. It delivers patterns that can be read incorrectly if we demand simplicity. So what do we do with anomalies that feel like they undermine the larger narrative? We hold two truths at once. The first, the long-term trend matters. It shapes sea levels, ecosystems, agriculture, and risk in ways that accumulate. The second, the day-to-day experience of weather can be chaotic, and that chaos can intensify as the system gains energy and shifts its circulation. In other words, a cold snap does not cancel warming. It exists inside it, like a sharp note inside a broader song. The deeper question isn't whether the planet is changing. It's how we, as humans, interpret change when it arrives in contradictory forms. If the sky can warm and cool in different layers at the same time, what does that teach us about certainty? And when the planet speaks in paradox, can we learn to listen without demanding it speak in straight lines? What if lightning could strike where there is no storm? High above the clouds, in the thin edge of air we barely remember exists. Most of us think of lightning as a local event, a summer afternoon, a dark cloud swelling with tension, thunder rolling like a warning. We understand lightning the way we understand fire, immediate, bright, grounded in the familiar world. But the atmosphere has hidden flaws. Above the weather we see, above the troposphere, where clouds build and planes cruise, there are layers where air thins, temperatures shift, and sunlight behaves differently. It's a place most of us never picture when we picture sky. And yet, in that upper space, brief flashes occur, luminous bursts shaped like jellyfish, columns, halos, and dancing tendrils. They have names that sound like folklore: sprites, elves, blue jets. For a long time, these phenomena existed mostly as rumors. Pilots spoke of strange glows above storms. People whispered about lights that appeared too fast and too high to be ordinary lightning. Scientists were skeptical, partly because the claims were hard to verify. The flashes were brief. They occurred in remote skies. Cameras in the right place at the right time were rare. Then, slowly, proof arrived. High-speed video and sensitive sensors began to capture these events. It turned out the atmosphere was doing something we hadn't fully accounted for. Electrical discharges reaching upward, not downward, spreading in rings at the boundary of space, igniting in the mesospheric darkness above thunderheads. It was as if storms had a second, secret life above themselves. This is not paranormal. It is physics. But it is also, undeniably, strange. Sprites can appear as red tendrils branching downward from a bright core, hovering high above a storm. Blue jets shoot upward from the tops of thunderclouds like luminous fountains. Elves are expanding rings of light, spreading rapidly in the lower ionosphere, triggered by the electromagnetic pulse of a lightning strike below. These events are categorized as transient luminous events, brief optical emissions in the upper atmosphere. They remind us that a thunderstorm is not confined to the cloud. It is connected to a larger electrical circuit that includes the ground, the atmosphere, and the ionosphere above. So where does the anomaly enter? It enters in the gap between what we think we know and what we actually measure. Even as these events have become more documented, they can still feel like exceptions, lightning that doesn't fit the mental model of lightning. And because they are associated with certain storm types, their occurrence can raise questions when they appear in surprising contexts, or when their frequency seems to fluctuate beyond what people expect. The atmosphere's electrical behavior is influenced by many factors: storm intensity, cloud top height, temperature profiles, moisture distribution, aerosols, and even larger-scale patterns like El Niño and shifts in circulation. Add to that the variability of detection, where cameras are, where satellites are looking, what instruments are active, and you have a recipe for uncertainty. Sometimes an increase in a phenomenon is partly an increase in our ability to see it, but that doesn't make it less real. In fact, it makes the story more human. We are living in an era where the planet's hidden features are emerging into view, not because they suddenly began, but because our eyes have changed. We have sensors that can detect faint glows in the upper atmosphere, satellites that watch storms from above, networks that map lightning across continents. The more we watch, the more the sky reveals. And what it reveals is a layered reality: weather below, electricity above, and an invisible interface where particles from the sun meet the edge of Earth's air. These upper atmospheric flashes also connect to something practical. They can influence radio communications, affect atmospheric chemistry, and interact with the ionosphere, the region that reflects and refracts signals, enabling long-distance communication. They are not just pretty anomalies, they are part of the planet's operational complexity. There's a poetic irony in that. We built our modern world on signals, satellite links, GPS timing, wireless infrastructure, and above the storms, in a realm most of us never imagine, the sky flickers with electricity that can, in subtle ways, touch those signals. So consider the storm again, not just as a cloud, but as a pillar, connecting Earth to the edge of space. The revelation here is not that the planet is haunted with mystery lights. It's that our categories, storm, lightning, sky, were too small. The atmosphere has been doing this all along, and we are only now learning the language. And that leads to a gentler kind of discomfort. If the sky can hide entire classes of phenomena in plain sight, What else have we been living under without noticing? How many of our certainties are simply the result of limited vision? And how many new anomalies will appear the moment we learn to look upward with better eyes? What if the ground beneath a city could sink without an earthquake, slowly, silently, like a tired body giving in to gravity? At first, it doesn't look dramatic. A doorway that no longer closes cleanly, a crack that reappears in the same corner of the wall, no matter how many times it's patched. A street that seems to hold rainwater longer than it used to. The kind of small inconveniences people blame on age, poor construction, bad luck. Then someone overlays old survey data with new satellite measurements, and the quiet inconveniences line up into a pattern. The land is dropping. In places around the world, the ground is subsiding, settling downward, sometimes by inches, sometimes by feet over years. It can happen in coastal regions and inland basins, in farming valleys and dense urban centers. The causes are often human and mundane, pumping groundwater faster than nature can replenish it, extracting oil and gas, draining wetlands, compacting soil under heavy development. Sometimes natural processes join in, amplifying what people started. But even when the causes are familiar, the consequences can feel like an anomaly, because we don't expect land to behave like a fluid. We build with the assumption that ground is a stable platform, not perfectly immobile, but reliable enough that we can treat it as a constant. Subsidence challenges that assumption. It reveals the Earth's surface as something more delicate, a skin stretched over porous layers dependent on pressure and water and time. Here's the uncomfortable part. When land subsides near the coast, the effect can mimic sea level rise, or rather, it can compound it. The ocean doesn't need to rise much if the land itself is sinking. A city can find itself lower relative to the water, even if the global sea level changes only modestly. Flood maps become outdated. Storm surges reach farther. High tides begin to creep into places that used to be safe. And because the descent is slow, it's easy to deny. People are not built to feel gradual motion. We adapt to it without noticing. That's why subsidence can feel uncanny when it becomes undeniable. When the first major flood arrives, when seawater pushes into streets on calm days, when foundations shift and utilities break. In some regions, the subsidence is patchy. One neighborhood sinks faster than another. Roads twist, pipelines strain. Buildings that were engineered for a stable plane suddenly sit on a tilted reality. The city becomes a mosaic of microgeographies, each with its own elevation story. How does this fit into a larger narrative about environmental anomalies? It sits at the crossroads of nature and human ambition. Water is life, but groundwater is also a hidden architecture. It supports the weight of soil grains, creating pressure that keeps layers from collapsing into each other. When that water is removed, the grains compact. The ground settles. Sometimes the settling is irreversible. The aquifer, once compressed, can lose its capacity like a sponge squeezed too hard. To the person pumping water, it's a practical decision. Crops need irrigation, people need drinking water, industries need supply. To the land, it is a structural change. And then, like so many environmental puzzles, the consequences ripple outward. As the ground drops, flood defenses must be raised, drainage systems must be redesigned, insurance maps must be redrawn. The cost is not only financial, it is emotional. It is the anxiety of living in a place where the baseline is moving. But there's also a deeper irony here. Subsidence is often the result of trying to stabilize life. A growing city needs water. A farm in a dry region needs irrigation. A community tries to secure its future by drawing from what lies beneath. In doing so, it changes the very ground on which that future stands. This isn't villainy. It's the complexity of survival. Science can map subsidence with remarkable clarity. Satellites can detect millimeter-scale changes in elevation. Engineers can model risk. Policymakers can regulate extraction, recharge aquifers, redesign infrastructure. But the hardest part is cultural. Persuading people that an invisible, gradual descent matters as much as a visible disaster. Because disasters are loud, subsidence is quiet, and quiet changes are the ones we most often misunderstand until they become irreversible. So stand for a moment in a city you love and imagine that the ground is not a floor, but a slow-moving surface. Imagine that stability is not given, but borrowed, maintained through careful balance between what we take and what we return. If the earth can sink without shaking, what other forms of motion are happening beneath our routines? And how many of our modern crises begin not with a sudden rupture, but with a slow agreement we didn't realize we were making with the ground? What if the forest could exhale a warning, subtle at first, then undeniable, written not in smoke, but in silence? There are places where the air smells like pine and damp earth, where the canopy filters sunlight into shifting green mosaics. In those places, it's easy to believe in stability. Trees stand for decades, sometimes centuries. Their growth rings feel like a calendar you can touch. You walk beneath them and feel time slow down. But forests are not just scenery. They are systems, breathing, exchanging, adapting. And one of the strangest signals a forest can send is not the sound of falling timber or roaring fire, but the quiet collapse of balance. It begins with small signs that are easy to miss if you aren't looking. Leaves browning earlier than usual, a subtle thinning of the canopy, a sudden boom in insects that used to be kept in check by winter cold or natural predators, patches of trees turning grey, then brittle like paper. In many regions, people have witnessed episodes of rapid tree decline, die-offs that seem to spread faster than expected. Sometimes the culprit is drought. Sometimes it's heat stress. Sometimes it's disease. Often, it's a combination. A stressed forest becomes a vulnerable forest, and then a single extra pressure pushes it beyond a threshold. From a distance, it can look like an anomaly, the forest simply giving up. But forests don't give up in the way humans do. They respond. They adapt when they can, and when they can't, they transform. The tension here lies in our emotional relationship to trees. We treat forests as permanent backdrops, as though their presence is guaranteed. Yet forests exist only within certain ranges of temperature, moisture, and disturbance. Shift those ranges, and the forest's identity can change. A familiar landscape can become unfamiliar within a decade. In some cases, die-off is driven by drought, intensified by warmer conditions. Trees need water, not just for growth but for survival. They pull water upward, like a delicate hydraulic system. When drought persists, the system can fail. The tree can't transport moisture. It becomes vulnerable to pests. Its defenses weaken, and pests, in turn, have their own relationship to climate. Insect populations that were once limited by cold winters can expand when winters soften. Beetles can spread across regions that used to act as barriers. Their life cycles can accelerate. The forest becomes not just stressed, but invaded. Then there is fire. Fire is not always an enemy of forests. In many ecosystems, it's part of renewal. Some trees evolved to tolerate fire, even to depend on it. But when heat and drought intensify, and when decades of land management alter fuel loads, fires can shift from ecological process to overwhelming force. They can burn hotter, move faster, and return more frequently than forests can recover from. The result is not just burned trees, but a changed future, soil chemistry altered, seed banks damaged, erosion intensified, new plant communities moving in. So why does this feel like an anomaly? Because it challenges the idea that forests are resilient by default. We love to say, nature bounces back. Sometimes it does. Sometimes it becomes something else. And that something else can reshape climate feedbacks. Forests store carbon. When they die or burn, that carbon can return to the atmosphere. When forests thin, they can absorb less carbon in the future. A shift in forest health can become a shift in the planet's carbon balance, a loop that is both biological and atmospheric. But even without the global feedback, the local human impact is immediate. Communities lose shade, water cycles change, streams warm, wildlife habitats fracture, people grieve landscapes the way they grieve loved ones, because place is part of identity. Here's the revelation hidden inside the forest's silence. Resilience is not infinite. It is conditional. A tree can survive drought, heat, pests, and fire up to a point. But stack those pressures together or make them more frequent, and thresholds appear. The forest crosses from endurance into transition. In science, transitions are described in terms of tipping points, regime shifts, ecological thresholds. In human terms, they feel like loss. But there's also a quieter kind of hope if we're willing to see it. Forests can regenerate, species can migrate, new compositions of trees can emerge. The forest may not return to what it was, but it can become a new living system, shaped by new conditions. That doesn't erase the grief. It just reframes the timeline, and it forces a question on us. If forests can change their identity within a single human lifespan, what does home mean in a world where the living background is no longer constant? When the trees around us become messengers of shifting conditions, can we learn to listen, not only with fear, but with responsibility and care? And if the forest can exhale a warning through its silence, what warnings are we ignoring simply because they arrive quietly? What if the ice didn't just melt? It moved, cracked, and carved with a rhythm that felt unfamiliar, like an old glacier learning a new language. There is a certain kind of silence you find near ice, not the quiet of absence, but the quiet of scale. A glacier doesn't announce itself. It simply exists, enormous and slow, like time made visible. You can stand beside it and feel that your lifespan is a brief flicker compared to its patience. And then you hear a sound that doesn't match the stillness. A deep crack, a low groan, the sudden thunderous collapse of ice into water. Calving is natural. Glaciers lose mass by shedding icebergs at their edges. They advance and retreat across centuries, responding to snowfall, temperature, and ocean conditions. But in recent decades, observers have described changes in the pace and style of glacial behavior, retreats that appear rapid, thinning that seems accelerated, collapses of ice shelves that once felt permanent. To many, this feels like the clearest proof of a warming world. To others, it feels like a story too large to hold emotionally. And to scientists, it is both, a measurable trend and a complex system with surprises. Because ice is not just frozen water, It is a dynamic material. It flows under its own weight. It fractures under stress. It interacts with rock below and ocean water at its edge. It responds to sunlight, air temperature, and crucially, what happens underneath. One of the most unsettling revelations in modern glaciology is how much the underside matters. Meltwater can pool on the surface, then find cracks and drain downward, lubricating the base of a glacier and speeding its slide toward the sea. Warm ocean water can creep under floating ice shelves, melting them from below, thinning the very buttresses that hold back inland ice. When an ice shelf weakens or collapses, the glaciers feeding it can accelerate, like a dam suddenly removed. This is not a single process, it's a cascade. So where is the anomaly? It appears when glaciers behave in ways that seem abrupt, non-linear, almost dramatic compared to the slow image we carry in our minds. A massive shelf disintegrates over weeks. A glacier's flow speed doubles. A hidden lake drains beneath an ice sheet. Crevasses proliferate like fractures in glass. Our expectations struggle to keep up. We often think climate change should act like a gradual fever, but ice can respond like a brittle structure under increasing load, stable, 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 then suddenly failing. That doesn't mean every collapse is unprecedented or purely driven by modern warming. It means ice is a system with thresholds, and thresholds can be crossed quickly once certain conditions align. There's a second layer of strangeness too, the relationship between ice and sea level. When floating ice shelves melt, they don't directly raise sea level because they're already displacing water, but they matter because they restrain land-based ice. When land-based ice flows faster into the sea level rises. The difference between those two facts is subtle in conversation, but enormous in consequence. So the story of ice is not just a story of loss. It's a story of acceleration. And acceleration has psychological weight. It means the future arrives sooner than the past prepared you for. Still, the ethics of storytelling matter here. It is easy to frame ice as a doom symbol. It is also easy to grow numb if the story is told only as a tragedy. The more human truth is somewhere in between. Ice is an indicator, a messenger, and a complex system that reminds us how interconnected Earth really is. A glacier's behavior depends on snowfall patterns far inland, on ocean temperatures shaped by currents thousands of miles away, on atmospheric circulation, on the physics of meltwater and fractures. It is a bridge between climate, ocean, and geology. When it changes, it is not just a local event. It's a signal in the planet's shared language. And for coastal communities, that signal translates into something deeply personal. The slow reshaping of shorelines, the risk of storm surge, the question of whether a city built on the edge of water can remain where it is. But perhaps the most haunting part is how ice carries memory. Glaciers contain trapped air bubbles, ancient atmospheres sealed in time. Ice cores allow scientists to read the history of carbon dioxide and temperature like a diary. And now, as ice retreats, that diary is literally shrinking. The archive of deep time is being thinned and fractured. So we are left with a paradox. We are learning more about Earth's past at the very moment we may be losing some of its most physical records. If that isn't an anomaly, at least in the human sense, it is a profound irony. So let's hold the image. A glacier carving, the crash echoing across water, the surface settling into ripples that spread outward long after the sound fades. The ice is moving. The world is moving. And the question becomes less about blame and more about relationship. If the planet's most ancient structures can shift in ways that surprise us, what does that say about our own timelines? How do we plan? How do we build? How do we live when the slowest parts of Earth can suddenly move fast enough for us to hear? What if the sea rose not only from the melting of distant ice, but from the sea itself swelling, warming, expanding, quietly taking more space, like a breath held too long? Most people picture sea level rise as a simple story. Ice melts, water pours into the ocean, shorelines retreat. That story is real, but incomplete. The ocean has another way of rising, one that is less dramatic to imagine, but just as powerful in the long arc of change. Water expands when it warms. It's a basic physical fact, almost too simple to carry the weight of global consequence. Heat the ocean, and it takes up more volume. Not because it gained new water, but because the water it already had begins to occupy more space. This is thermal expansion, sometimes called steric sea level rise. It's the ocean's quiet inflation. If you want to feel how strange that is, hold a glass of cold water in your mind. Now imagine that glass warming slowly, imperceptibly. It doesn't look different. It doesn't taste different. But at the molecular level, it relaxes, spreads, becomes slightly less dense. Multiply that tiny change by the entire ocean, and you get coastline-altering reality. Here's where it becomes an anomaly in the public imagination, because thermal expansion doesn't fit our instinctive narrative of cause and effect. It's hard to picture warmth as more water. It also feels unfairly subtle, an invisible process with visible consequences. People understand a glacier melting. It looks like loss, but water expanding feels like a trick. The sea rises without obvious drama, like a slow claim, and it doesn't rise evenly. Sea level change is not a uniform bathtub filling up. It varies by region, due to ocean currents, wind patterns, gravitational effects, and land movement. Some coastlines see faster rise, others slower. Some experience temporary drops, then surges. The sea behaves like a living surface, responding to forces that range from weather to deep circulation. That regional variability can feel like a contradiction. One more, how can this be happening here, puzzle in a world already full of them? A community might see more frequent flooding while another, across an ocean, sees less change for a time. People mistake local variability for global cancellation, and the confusion spreads. The science, again, is not broken. The system is complex. Thermal expansion also connects to another quiet truth. The ocean absorbs most of the excess heat trapped by greenhouse gases. The atmosphere warms quickly and grabs headlines, but the ocean is the planet's main heat sink. That heat doesn't vanish. It settles into layers, moving slowly downward through mixing and currents stored like a long-term savings account of energy. And stored energy changes behavior. Warmer oceans can fuel stronger storms. They can alter marine ecosystems. They can contribute to coral bleaching. They can shift fish migration. And yes, they can rise simply by expanding. There is something deeply human about overlooking this mechanism. We are visual creatures. We trust what we can see. Thermal expansion asks us to trust what we can measure instead. Minute changes collected over decades, translating into major shifts. Imagine a tide gauge on a pier, recording sea level day after day. For years, the line wobbles with tides, storms, and seasons. Then, over decades, the baseline creeps upward. The gauge becomes a witness to a change too slow to feel in a single afternoon, but too persistent to deny in a lifetime. In the modern era, satellites add another perspective. They measure sea surface height from space, tracking global patterns with remarkable precision. Those patterns show a world where the ocean surface is not flat but shaped, higher here, lower there, by currents and winds. As warming continues, those shapes can shift. This is where thermal expansion becomes more than a physics detail. It becomes a lens. It tells us that climate change is not only about adding or subtracting things, more carbon, less ice. It's also about changing the state of what's already here. The ocean's molecules are responding to heat. The sea's baseline is responding to energy. And energy, unlike water, can move through systems in ways that feel intangible until they arrive at the shoreline. The revelation is quiet. The ocean doesn't need more water to rise. It only needs more heat. But the reflection is heavier, because it means sea level rise can continue even if ice loss slows, as long as the ocean remains warm and continues absorbing heat. It means the sea has momentum, not moral momentum, but physical inertia. Once heat is stored in the ocean, it doesn't leave quickly. The system carries its past into the future. That's the way Earth often works, not with instant switches, but with lagging responses, with long echoes. So walk along a beach and look at the line where wet sand meets dry. Imagine that line shifting, inch by inch, not with a sudden flood, but with a patient claim. Imagine that part of the rise comes not from distant ice, but from the ocean itself, expanding as it warms, like a lung holding more air. What does it mean to live beside a sea that can rise simply by changing its internal state? And if heat can transform the ocean's volume, what other transformations are already unfolding, quietly, invisibly, inside the systems we thought were stable? What if the air you breathe carried an extra kind of heat, not just warmth, but dryness, turning familiar summers into something sharper, more exhausting, more dangerous? There's a moment in certain heat waves when the world feels altered. The sun is bright, but the brightness doesn't feel cheerful. It feels aggressive. The shade doesn't cool the way it used to. Even the wind, when it arrives, feels like it's coming from an open oven. People often describe this as, it's not just hot, it's different. That difference has a name: the relationship between heat and moisture. Human bodies don't simply need cooler air. We need the ability to release heat. We do that through sweating, which works by evaporation. When the air is dry enough, sweat evaporates efficiently, cooling us. When the air is humid, evaporation slows, and the body's internal temperature can rise dangerously. But there's another twist, one that can feel like an anomaly, because it doesn't match the cliché that humidity is the worst. Extremely hot, extremely dry air can also be brutal, not by blocking sweat evaporation, but by pulling moisture from the body and landscape with relentless speed. It dehydrates people, it stresses plants, it dries soils, it primes forests for fire. It can turn a heat wave into a multi-system crisis. This is where the concept of dry heat becomes more than a comfort joke. It becomes a climate stressor. In some regions, heat events are arriving with unusual combinations: record temperatures paired with exceptionally low humidity and strong winds. These ingredients don't just make it uncomfortable. They raise the risk of rapid fire spread, crop stress, and dangerous conditions for anyone working outdoors. They can also produce a sense that the climate has shifted into a new mode, because the heat feels less like a temporary weather pattern and more like a new baseline. The anomaly is not that heat waves exist. They always have. The anomaly is the intensity, the duration, and sometimes the compound nature. Heat plus drought plus wind plus dry vegetation, stacked like kindling. Climate science explains part of this clearly. As the planet warms, the probability of extreme heat increases. But the way that heat expresses itself locally can vary. Some places become hotter and drier, others become hotter and wetter. Some see greater variability, swinging between heavy rain and severe drought. That variability, again, can look like contradiction, but it often reflects a system with more energy and altered circulation. Consider what happens when soils dry out. Moist soils can cool the air through evaporation, water turning into vapor, consumes heat energy. Dry soils can't do that as effectively. More of the sun's energy goes directly into heating the air. This creates a feedback loop. Dry soil leads to hotter air, which dries the soil further. In agricultural regions, this can be devastating. Crops rely on a delicate balance of heat and water. Too much heat during flowering can reduce yields. Too little soil moisture can stunt growth. And if irrigation draws heavily from groundwater, the situation can connect back to land, subsidence, and water scarcity, weaving multiple anomalies into one lived reality. Heat also changes behavior. It changes how cities function, how people sleep, how power grids strain under demand for cooling, how emergency rooms fill with heat-related illness. It changes the social fabric. Who can afford air conditioning? Who must work outside? Who lives in older housing that traps heat overnight? One of the quietest and most dangerous aspects of modern heat is the warm night. When nighttime temperatures stay high, the body doesn't recover. The city doesn't cool. The stress accumulates. Heat becomes not just an afternoon discomfort, but a continuous pressure. People wake up tired, irritated, drained. Over days, the risk rises. This is where heat becomes less like weather and more like an environment. And in some places, people report a new kind of summer, longer, harsher, with fewer relief days. The seasons blur. Spring feels shorter. Autumn arrives late. The calendar loses its old reliability. Is that perception always accurate? Not always. Memory can distort. One bad summer can imprint itself like a myth, but long-term data in many regions supports an increase in heat extremes. The lived experience is often rooted in something real, a shift in probability, a change in baseline, a growing frequency of unusual days. So what's the revelation? That heat is not a simple number. It is a relationship between temperature, humidity, wind, soil, shade, infrastructure, and human bodies. A few degrees can mean the difference between tolerable and dangerous, between a dry landscape and a flammable one, between a normal summer and a season that feels like an endurance test. And what's the reflection? That the planet's changes are not only about distant ice and faraway oceans, they are about the air that touches your skin. If heat is becoming more intense and more complex in the way it interacts with moisture and land, what does that mean for how we design our cities, our work, our daily lives? And if the atmosphere can deliver heat in combinations that feel newly hostile, what other ordinary elements, air, water, soil, are quietly shifting into unfamiliar forms around us? What if the rain that falls from the sky carried a faint chemical signature of our modern life, so diluted you'd never taste it, yet persistent enough to show up in places that feel untouched? Imagine standing on a ridge high above the tree line. The air is thin and cold. The view stretches into a horizon that feels prehistoric. You'd think this is the kind of place where human influence fades into the distance. Then you learn that even here, in rain and snow, traces of industrial compounds can be detected. Chemicals that travel invisibly on winds, hitching rides on dust and vapor, circling the globe. It's the kind of fact that can make a person pause, not because it's sensational, but because it feels intimate. It suggests that what we make does not stay where we make it. One class of compounds, often discussed in this context, is long-lived synthetic chemicals used in products ranging from industrial processes to consumer goods, substances valued for their stability, their resistance to heat and degradation. That stability, once a selling point, becomes a defining risk. When these chemicals enter the environment, they can persist and spread. The anomaly is not that pollution exists. The anomaly is the reach. People have long understood that smoke can drift, that rivers carry runoff, that cities affect their surroundings. But the idea that certain substances can be detected in remote precipitation, far from factories, far from highways, forces a new understanding of local and global. It suggests that the atmosphere is not just weather. It is a transport network. There's a scientific reason this happens. Some compounds can evaporate or attach to airborne particles, travel long distances, then deposit through rain or snow. Others can cycle, evaporating, condensing, and redepositing like a chemical echo that moves with seasons. Mountains and polar regions can become collection zones, as cold temperatures encourage certain chemicals to condense and settle. It's a process that is both physical and quietly poetic, the planet sorting what floats and what falls. But the human response to this information can swing between despair and numbness. It's easy to think, if contamination reaches everywhere, then nowhere is safe. Or, conversely, if the amounts are tiny, why care? The truth is more nuanced. Environmental risk isn't always about immediate toxicity. It can be about accumulation over time, about how substances behave in bodies and ecosystems, about how small exposures add up across populations. It can also be about equity. Who is exposed more? Who bears the burden? Who has the power to reduce sources? Yet this story is not here to moralize. It is here to reflect on what it means to live on a planet where our chemistry can become part of the rain. There's an irony in how we often define progress. We celebrate materials that last, stain-resistant fabrics, non-stick surfaces, coatings that repel water and grease. We build durability into our objects because durability feels like reliability. But in the environment, durability can become persistence. Reliability becomes longevity. And longevity becomes a kind of haunting. The revelation here is not that we are doomed. It is that the atmosphere connects us more deeply than we like to admit. Every breath is local, but the air itself is global. The particles over your town today may have passed over deserts, oceans, industrial regions, forests, and farms within days. The rain in a mountain basin may carry the faint story of distant manufacturing, distant combustion, distant choices, and the reflection becomes personal. We are used to thinking of the environment as out there, a wilderness, a coastline, a rainforest. But the environment is also inside lungs, inside bloodstreams, inside the food chain that links soil to plant, to animal, to human. When scientists detect trace compounds in remote places, it can feel like the planet is handing us a mirror, not to shame us, but to show us the true scale of our footprint, not only in carbon and heat, but in chemistry. The question, then, is not only how to reduce contamination, though that matters. The question is how to live with the knowledge that our inventions travel. If the rain can carry subtle signatures of human industry to the farthest corners of the world, what does responsibility look like in a system where nothing truly stays contained? And in a century defined by materials built to last, how do we decide what should endure and what should be designed to disappear? What if the strangest anomalies weren't in the sky or the sea, but in the way we decide what we're seeing? How certainty forms, how doubt spreads, how the same data can feel like two different worlds. By now, we've traveled through puzzles that live in different layers of Earth. A magnetic pole that drifts, rivers of moisture in the air, oceans that rearrange their heat, forests that thin and transform, ice that fractures into motion, heat that sharpens, chemicals that ride the rain. Some of these are well-established phenomena. Some are contested interpretations. Some are a mix, real signals wrapped in public confusion. This chapter is about that wrapping, because an anomaly is not only a thing that happens, it is also a story we tell about what happened. And in modern life, stories travel faster than oceans, faster than glaciers, faster than the core of the Earth. We live in an age of measurement, satellites, sensors, models, networks of data that watch the planet like a pulse monitor. That should make truth easier. Sometimes it does, but it also creates a new kind of tension. The more data we have, the more choices we face about what to trust, how to interpret, and how to communicate uncertainty. Science is careful by design. It speaks in probability and error bars, in confidence intervals, in evidence suggests, and more research is needed. This isn't weakness, it's humility made method. But humility is hard to sell in a world addicted to certainty. So the public conversation often splits into extremes. One side treats every unusual event as proof that everything is spiraling. The other treats every unusual event as proof that nothing is happening. Both responses are, in their own ways, a refusal to tolerate complexity. The truth is that Earth's systems include variability. They include natural cycles, random fluctuations, and long-term trends. The challenge is not to choose between everything is normal and everything is unprecedented. The challenge is to understand which changes are signals, which are noise, and which are normal processes now amplified by altered conditions. That is not an easy task, even for experts. And it becomes even harder when the conversation is shaped by fear, fatigue, identity, and the human need to feel in control. Here's a quiet fact about anomaly detection. It depends on baseline. To call something unusual, you must know what usual is. That means you need long records. You need consistent measurements. You need context that spans decades or centuries. But for many Earth systems, our high-quality global records are relatively recent. Satellites have only watched the whole planet for a few decades. Deep ocean monitoring is still incomplete. Even ground stations can be sparse in remote regions. So sometimes we see something that looks unprecedented simply because we haven't been watching long enough. Other times, the opposite happens. We dismiss something real because it feels like it could be normal variability, and we underestimate how often the system has shifted in the past. This is where the cultural meaning of anomalies becomes as important as the physical reality. An anomaly can be a warning, but it can also be a mirror. It reflects our biases, what we fear, what we deny, what we believe is stable, what we think should happen. In storytelling, we often want a villain, a single cause, a simple narrative arc. But Earth is not a novel. It is a set of overlapping processes. Human influence is significant, but it interacts with natural variability in ways that can produce surprising local outcomes. The ocean can warm overall, while a region cools temporarily. A warming climate can still deliver snowstorms. A forest can burn from a lightning strike in a drought year, and that drought may be influenced by long-term trends and short-term atmospheric patterns at once. The honest story is layered, and layered stories demand a certain kind of listener, a person willing to hold uncertainty without turning it into cynicism or panic. So how do we talk about anomalies ethically? We start by separating three things. First, the phenomenon itself. What was observed? What was measured? Second, the interpretation. What do scientists think it means, and how strong is the evidence? Third, the emotional story we attach to it. Does it make us feel afraid, vindicated, helpless, curious? When those three are tangled together, the public conversation breaks down. People argue not just about facts, but about feelings disguised as facts. The most human insight in all of this may be that uncertainty is not the enemy of truth. It is part of truth. A mature relationship with the planet means accepting that some questions take time, some systems behave in non-linear ways, and some phenomena are only understood after years of patient observation. The lesson is not to stop caring. The lesson is to care with clarity. We can be concerned about ocean circulation without declaring imminent collapse. We can acknowledge magnetic drift without turning it into myth. We can take heat extremes seriously without pretending every heat wave is identical. We can treat chemical persistence as a real issue without surrendering to hopelessness. This is not just about science. It's about adulthood in a complicated world. So here's the final question before we close. If the hardest part of understanding Earth's anomalies is not the data, but the meaning we assign to it, how do we become better interpreters? And in a world where uncertainty is often weaponized or sensationalized, can we learn to treat not fully known yet as a space for curiosity rather than a reason to stop listening? What if the most important anomaly is this, that we are capable of knowing so much about Earth and still being surprised by it? In the end, the story we've been tracing is not a catalogue of mysteries meant to frighten us. It's a portrait of a planet in motion, and a portrait of the human mind trying to keep pace. We began with an idea so familiar we rarely question it. North. We learned that magnetic north is not a fixed promise, but a drifting point shaped by a restless interior. That alone was enough to unsettle the notion of permanence. Beneath our streets and cities, the planet is alive with motion we do not feel. Then we looked up. We found rivers in the sky, corridors of moisture that can feed landscapes or overwhelm them. We found lightning above storms, brief, luminous events flickering at the edge of space, reminding us that even a thundercloud has a hidden life. We realized the atmosphere is not only the air around us, but a layered electrical global system that carries water and chemicals and energy across boundaries we imagined as borders. We looked to the ocean and met its complexity, currents that carry heat like memory, surfaces that rise not only from melted ice, but from warmth itself. The sea is absorbing the planet's excess heat, expanding quietly, changing its moods in ways that ripple into weather, ecosystems, and shorelines. The ocean taught us that invisibility does not mean insignificance. Some of the biggest changes happen below the surface. We walked through forests that once felt steady, and we heard the silence of stress, drought and heat and pests and fire combining in ways that push ecosystems toward thresholds. We watched ice, ancient and patient, respond in sudden fractures and accelerations, showing that the slowest parts of Earth can still change quickly when the conditions align. We moved through heat that feels newly sharp, through air that dries out bodies and landscapes, through nights that no longer offer relief. We felt the intimate truth that climate is not only global averages, but lived experience, how a day feels, how a city breathes, how a body copes. And we confronted the invisible reach of chemistry, the way certain compounds can travel on winds and return in rain, blurring the line between remote and touched. We saw that modern life does not stay neatly contained within the places where it is manufactured. Finally, we turned the lens back on ourselves, on interpretation, on baseline, on uncertainty. We admitted that an anomaly is not just what the planet does, but what we notice, and what we choose to believe about what we notice. So what thread ties all of this together? It's not doom, it's not denial, it's humility. The Earth is an old system with deep feedback loops and long memories. We are a young species with extraordinary tools and a short cultural attention span. Our instruments can see farther than our instincts can process. We can map moisture plumes across oceans and measure millimeters of land subsidence from space, yet still struggle to translate those measurements into the slow, steady changes required in how we live. And there is a tenderness in that struggle, because beneath every chart and forecast is a human longing for stability. We want seasons to arrive on time. We want the shoreline to stay where we learned it. We want forests to remain green. We want storms to behave like storms always behaved. We want the future to look like a slightly edited version of the past. But the past was never as stable as we imagine. It only felt stable because we lived within a brief window of time, and because the planet's rhythms were for a while predictable enough to build civilizations around. Now, predictability is becoming a more fragile resource. That fragility doesn't mean the world is ending. It means the world is asking us to mature, to replace the fantasy of control with the practice of stewardship, to replace the hunger for absolute certainty with a more resilient form of understanding, one that can hold complexity without collapsing into despair. The point of telling these stories is not to turn the listener into an expert, but to turn the listener into a witness. A witness notices. A witness asks better questions. A witness understands that care begins with attention. So here is the final, timeless question, to leave hanging in the air like a bell that keeps ringing after it is struck. If the planet's anomalies are invitations, inviting us to look again, to learn again, to admit what we don't know, what kind of people do we become when we accept that invitation? And if Earth will always remain, in some ways, mysterious, can we build a future not on the illusion of certainty, but on curiosity, humility, and the courage to keep listening?